Hi everyone. So we're going to start review at this point in the year, and we're going to review the material for a couple reasons. Some of you need to take the Regents exam to get credit for the course, so that'll be very important for you to pay attention to all this review. And those of you who don't have to take the Regents exam, the review is going to be good for obviously covering the information again, because you never know when in the future you might need to have this background knowledge. If you plan on taking other science electives, or for some reason you want to go into the sciences when you graduate, you're going to need to know this information. So let's begin. You guys, you should have in your possession these notes here. This is your student note sheets. We're going to go through a topic every day, and you're going to fill in as I go through the PowerPoint. And then after we're done with each topic, you're going to have a set of homework questions that are in Schoology. So you should have out this packet, and I'm going to go through my PowerPoint. So we'll begin. So this is what you absolutely need to know to pass the Living Environment Regents exam and for other things. So just for those of you who are taking the exam, this will be good for you to know. The exam consists of about 85 questions. There's 85 points on this test, and it's broken down into 4 parts. There's Part A, which is 30 multiple choice questions. Part B also has about 30 multiple choice questions, and there's like a Part B1 and B2. There is a graph on this section of the test, so definitely be prepared for that part. Part C is going to have short answer questions dealing with your ability to apply what we've learned this year to different types of situations. And then Part D refers back to the 4 state labs. Now, we didn't do all of the state labs the way that they were originally written, but we did cover the content for each one of them. And so when you're taking the Regents exam, make sure you have, you're going to need a pen and pencil with you. Almost all of your answers need to be in pen, except for the graph or any drawings that you might have to do. Those you're allowed to do in pencil. All right, so let's move on to our first topic, the scientific method. So some terms to know: observation, that's what is seen or measured. And an inference, that's a conclusion based on observation or evidence. So, for example, an observation could be, there's puddles in the parking lot. The inference you could make is that maybe it had just rained, because you have past experience with puddles. Usually that's why there's puddles in a parking lot. And then a hypothesis is a prediction based on available evidence. A good hypothesis will state both the cause and the effect. And it should be able to be tested. If you can't test it, then it's not written in a correct way. And you have to be able to use an experiment. The best way, or the easiest way, is to write it as an if-then statement. For example, if I give patients this pill, then they will not get sick. It shows both variables that are going to be involved in the experiment, and it kind of tells whoever's reading about the hypothesis what you're thinking about. A theory is an explanation of natural events that is supported by strong evidence. So a theory in science is a very certain thing. The way we use the word theory in everyday language is a lot less certain. It's more just like your opinion or an idea. Theories will tie together many scientific facts, hypotheses, and laws, like the theory of evolution. There's some misconceptions, though. Theories are things that are opinions or are not proven. So this is an incorrect use of the word theory in a scientific context. A scientific theory is not just a simple guess or conjecture, and it's strongly supported by evidence. Okay, moving on to a controlled experiment. They will compare the results of an experiment between 2 or more groups. You're going to have an experimental group. This is the group that you're testing. it's receiving the treatment, that's the one that you're changing the variable with. And then you should always have a control group to compare your experimental group to. It needs to be identical to the experimental group in every way except for one. It's that independent variable that changes. So it does not receive the new treatment. Only the experimental group will. A placebo, sometimes they use it in reference to like a sugar pill, or it's another fake treatment. Sometimes in a group, they'll give half the people the real thing and the other half a placebo, which is not, it's like, sugar water or something like that. Because sometimes, the human mind can be pretty strong, and if you convince yourself of something, it can change the results of some experiments. So they kind of do this, kind of unknown or blind testing so that nobody knows if they have the real thing or the fake thing, and they can get more accurate information that way. Then, like I said before, the independent variable is a variable being tested. That's what the scientist is changing. So you could be testing a new drug, a new fertilizer, and it's going to be the if part of an if-then statement. For example, the one we said before, if I give patients the pill, then they will not get sick. So the pill is the independent variable. And when you're graphing it, it's always placed on the x-axis, so on the horizontal or bottom axis. Then there's the dependent variable, and this is the one that you measure. This is your data. So remember, dependent and data both start with D. And this is the result. This is what we measure and end up with. And it's going to be the then part of the if-then hypothesis. And you're going to plot it on the y-axis when you're graphing it. So on our data table here, we have temperature versus heart rate. And so you can label on your data table that the temperature is going to be our independent variable. So you can write independent variable at the top, or you can write ID for short. This is the part that you're changing. We're going to change the temperature to see what happens to the heart rate. So heart rate is our dependent variable. This is our data. This is what we're measuring. You're going to, if you were to graph this, the temperature goes on the x-axis, heart rate goes on the y-axis. All right, let's talk about some characteristics of a good experiment. It has to be repeatable. You have to be able to repeat it and get the same results every single time, or very similar results. You should definitely have a large sample size. More is better. 10 people or 100 people, out of those two test groups, 100 is going to be better. You're going to get more reliable information that way. And you should also perform it for longer periods of time, because sometimes time will tell more about the data than doing it in a short period of time. So we're in the middle of people, getting vaccinated. And the more people that get vaccinated, and the longer time we have to study this coronavirus, the more information we're going to have and be able to make better predictions about future pandemics. You only want to test one variable at a time. All the other characteristics of tested groups should be the same. If you change too many variables, then you don't really know why you're getting the results that you're getting. So just always change just one, keep the rest the same. And an experiment should be peer-reviewed by several scientists so you can determine its accuracy. You need to have other people look at it and make sure it's not, you don't have incorrect information or incorrect data. And you have to test the hypothesis in an experiment to show whether it's wrong or right, or supported or refuted. And it needs to be explained within your experiment, how you're testing the hypothesis and how you know if your results support it or don't. Your experiment has to be objective, so you can't have your opinion inserted in there. The experiment and conclusion should be fair and unbiased. Fact and opinion cannot be mixed in an experiment. It has to all be based on facts. The experiment should follow established ethical and legal standards. You can't test on deadly things on people or animals or things like that because it's not ethical. So it has to follow certain guidelines. All right, so now when we've done an experiment, we've got to do something with the data. So we're going to make data tables and graphs. Data tables are used to organize data, and later it'll get plotted on a graph. The first column in the table is for the independent variable, like we said before on our data table, and the second column is usually for the dependent variable. Each column needs to have a title, and it should have units. Sometimes you have to label a data table, so you always have to make sure you've got, what it is that you're testing and the unit if needed. The data in the table should be arranged in ascending or descending order, meaning, smaller to larger or larger to smaller. And then both the x and y axis of the graph have to be labeled or titled with the exact same information from the data table. And these labels are typically, like I said, the same ones as used in the data table. Once again, you have to make sure you include your units. The independent variable is always plotted on the x-axis, that horizontal part. And the dependent variable is always plotted on the y. The x and y axis should be numbered. And the numbers have to increase by a uniform increment. That means each line goes up by 1, by 2, by 5, by 10. And your scales should take up most of the axes. You want to spread your data out as much as possible because squeezing it into the bottom corner makes the graph impossible to read, and we won't be able to give you credit on the graph if we can't read your data points. The numbers have to line up with the grid lines of the graph, not the spaces between them, unless it's a bar graph. If we're doing a line graph, then they'll usually always tell you, do a line graph, do a bar graph. But if you're doing a bar graph, then the numbers go in the columns. But if it's a line graph, you have to be even with the lines of the grid that they give you. You don't need to start your numbering at 0. If we're using years, for example, and we start with 1900, then 1910, 1920, you don't want to start with year 0 because then you'll have to put a break, and they don't allow you to have breaks on science graphs. We end up marking that scale incorrect if you put a 0. So sometimes if you're not sure and it's not really on your data table, just leave off the 0, and we won't assume that there's a 0 there unless it's part of your data. And to date, most graphs drawn on the Regents exam are line graphs. If you draw a bar graph when they wanted a line graph, then you lose credit for the whole thing. And all points plotted on your graph have to be surrounded by a circle. Sometimes they want a square or triangle. Depending on how many lines you have to graph on there, you have to differentiate them. And the reason they ask you to put a circle around your data points is that sometimes you end up having a stray mark on your graph. And if it looks like another data point, you may end up losing points. So if you put a circle around your data points, then we know that was intentional, and then we know exactly what you meant to show as your answer. All right, so here is an example of a graph. This is the temperature versus heart rate. On the bottom, you can see temperature, that's our x-axis, that's our independent variable. It's got our unit. The lines are numbered. They did skip every other line, which is okay, and it's just easier to number sometimes that way, but every line increases by 2.5 if you look. I'm sorry. Yeah, no, that is true, by 2.5. So the line in between 0 and 5 would be 2.5. Then the line between 5 and 10 is 7.5, and so on. And then on the y-axis with heart rate, it's increasing by 20s. Each line is worth 20. So the only thing that this graph would be missing is a title. Sometimes they do ask you to come up with a title or to write a title. And if you were to write temperature versus heart rate, depends on how the question is asked. But usually, if you phrase it as the effect of temperature on heart rate, that's a more accurate title. So if you can format it that way with the effect of blank on blank, and it's usually the x-axis and then the y-axis written in the title, you'll have a better time, coming up with an accurate title that way. And that takes us to the end of the scientific method.